Hey, welcome back. So, yeah, I had a short break and I thought a little bit how to proceed. Actually, I planned to continue with more visual stuff and exploration for the demo, but then I reconsidered and thought about that A, there are a bunch of issues with the current compute shader implementation, and B, it might be helpful even outside of the context of the demo to see how go about implementing and actually refining compute shaders and effects. So maybe this might be helpful for you guys to actually implement your own shaders and yeah, effects. So let's spend the next hour or so to refine this particle effect and implement its missing features. So the first thing we noticed that is that if we move the center of this force, then yes, we see that certain points are being reconstructed, but we see up there the reconstruction is being loosened, and if you move there, it's reconstructed. But we see that there are a lot of gaps, and these gaps come from the fact that we are using the current point position to determine whether or not these points are inside the reconstruction volume. And obviously, if these things are scattered all over the place, eventually all of them will be out of range for reconstruction. So, if we zoom in out here, so yes, these points there, out there, they will never be reconstructed. So obviously, we have to do something about this. I thought a little bit what to do there, and my idea is that we add an option to either use the target or the mid position for determining the distance, or the actual position, so the current mode. So we have a mode toggle basically. Should be straight enough to implement. Another thing would be that currently we have this falloff mode here. Or it's not really a mode, it's more a parameter. And this falloff mode, I think it doesn't really work as you would expect it to be working. So I think we have to do something with this. First, we have to visualize it, and then we have to figure out like how do we actually compute the falloff, and what's the formula behind that. And then obviously we have to figure out a better way to render these gizmos here so we understand what's going on with the falloff. So and maybe we find some time to actually do the whole thing with the radius distance that we set out to do earlier. So let's get started. First, let's start with this additional parameter we want to use there. We can go into reconstructor force and add a new input parameter. And this is, so we now have a bunch of options here. So we can use a Boolean, but to be frank, I prefer nowadays integers, because then we can give these integers a like a enumeration dropdown, and it will make the parameter easier to understand. So let's give this, let's think about a name. Maybe we name this distance mode. And yes, the compilation engine needs to run for stream. And so let's compute this, convert it into float, add it into our parameters buffer. Then we go into our shader. Oh, close the shader. So let's do visual code here. I think we don't need this. We don't need a wider for now. Here's our source code from earlier, reconstruct the force, and we have to add the float distance mode, and then we add so So we have to be careful. So we basically take the position and volume. It can either be so the position and volume is, yeah, we transform this guy here and let's add a new temporary variable called used pose equals, and then we say if the distance mode is below 0.5, then we use the position. Otherwise, we use the target points position. And then we take the used positions and we convert this into the position and volume. And from this, we calculate the distance. So let's see what's happening here. So now if we change this mode parameter to 1, we should see an effect. Nothing is happening. Boo, boo. I hate you. So we have a bunch of more parameters here that we don't really. So like what is all this thing? So we have the bounciness attraction maximum. I think we don't need this. And we don't need this. I think like having some kind of strength parameter is actually a good idea. And select mode, I think we don't need that either. So there is a bias here, which we can later use to, let's see, I wonder if this is the same bias we use for the randomize points function we used earlier. So we can check this with the volume shape, which we don't use right now, but we can use later. I think having a strength parameter is actually a good idea. So we can multiply this later, and a portion we don't need. Yeah, and so if you compile this, some stuff is happening, but I think right now it's a little bit too much. So whatever is going on there, this is not what I expected. So, and I think we have to really remove all these parameters here that we don't need. The same thing. So we think we don't need a phase, we don't need a threshold, we don't need the volume shape right now. The bias might come in handy eventually. The strength we had. We don't need the mode. The soft edge can go. The Gizmo visibility, we can move this to the bottom. We don't need bounciness, attraction decay, max acceleration. But we need the target points and the distance. Okay. And a little bit hard to see, but so currently we only have 4 parameters going into our float buffer here. This looks kind of, oh, actually seems to match. So 4 parameters there and 4 parameters here. So let's condense this a little bit. Maybe we can move the target points a little bit further down. And I guess we can squeeze this a little bit here. A bit hard to see if it's not evaluated all the time. Workaround to pass. Yeah, I think this is not a workaround. This is a completely valid thing to do. Go away, you comment. So there's a couple positions. We have int to buffer. Do we have an int buffer there? Let's check our code. No. So we can clean this up as well. And then I guess we can, wait a second, this we can use later. I think we can connect this actually. It's a good idea. And then we have the gizmos down here. we have this target mode that we need to add the correct things here. Okay, so we cleaned this up a little bit. I think if we move this, it should instantly give some effect, which it doesn't. So we have to look into this, why it's not working. So maybe we start from scratch by emitting. But these guys seem to be doing something. And if I seems to be doing something here, but wait a second, we should use target mode to 1. That's what we initially set out to do. And yeah, I think it this seems to work. So no matter how far they are away, if I bring this close enough, it will reconstruct the original thing, which is nice. And I think from now on, we don't need this connection line here anymore. I think this is rather confusing. So, okay, getting there. So the next thing we want to do is to have a proper visualization of this falloff thing here. And I think this sounds easier than it is. Because I did it a bunch of times and it's actually for me rather confusing because there are a bunch of different ways how to apply falloff radiuses, whatever that's called. And to clean up my mind on that one, I spent some time in Desmos to do a little bit of visualization here. And let's switch over to Desmos. So desmos.com, if you don't know this, if you do anything with creative coding, I think you should really invest an hour or two into that tool. It's super, super helpful. And it really helped me to play with mathematics. So I suck with, I'm very bad with mathematics. And so the only way I can understand mathematics is by actually playing around and seeing visualizations of what's going on. And here the idea is that, so maybe we duplicate this side here and start with, let's save this guy here. And, like the idea is that you have normal, things like in school mathematics. So you might have like a sign with from X or something like this. The cool thing is that you can use other characters than X and Z, and they immediately will turn into parameters. And this is like super cool because this is just like a very handy way to explore different means of like exploring how formulas work. And coming back to this thing here, What's nice is that you can do, for instance, like you can have like, you can also do automatic things like, give me, I think this should be like, can you do this? It's one where X is. So if we take this guy here, this formula, and we say, okay, give me so put me a line every time we have like this value is 0. So this could also be like super helpful to actually visualize the thing, and then you can go in here and just, for instance, it's a little bit hidden. I just found this out today, but you can adjust the line width and stuff of these helper lines. So going back to Desmos here. So what I did here was from the internet, I copied this formula for smooth step. So smooth step is the big red line we see there. And this formula is also available in shaders, and it's the book of shaders tells a lot of the smooth step function, how nice this is. And you added two parameters here. So the one is the radius of our volume. So if the radius is 3, then we see we have a circle here of 3. And if the falloff is 0, then the idea is that the result is 0, 0, 0, 1, 1, 1, 1, 1. And if the falloff is a little bit bigger, then this is in percentage of the radius. And this means that if we increase the radius respectively, we can basically the falloff factor, the shape of the thing stays the same. This is a little bit different than other implementations in Tooll, where the falloff is being added towards the radius, but I think this is easier to get under control. And one thing you saw this already, if the falloff is negative, then the shape inverts itself. So it will be 1 inside and 0 outside. And this probably this is the default expected behavior. So I guess everywhere we have the F, we should invert this, or maybe we should just invert this guy here. So earlier I mentioned that it would be nice to have an option to flip between inside and outside. So now the flipping is implicit because we could have a negative falloff thing. And everything else is just like me messing around with stuff. So we have like this, the blue circle here and the green circles is just like a visualization of like the shape. And these guys here are these orange lines to say, okay, like this is the beginning and the end of the falloff. And this thing here is me trying to figure out this red line that I guess this should also be 1 minus, so it's like a bit easier. Maybe not. And I'm kind of confused. If this is, yeah, I think it should be. Let's move this. Go back here. So like, let's leave these scale. So this is just me playing around with a formula to have these lines, this line being at 1 at the inner falloff radius and at 0 at the outer falloff radius. And I don't even know like why why this is so complicated. I'm pretty sure like what does this do? I think this could be just like a multiplication. And let's go like if we have, let's try to clean this up a little bit. So nice thing is like, just typing will give you an immediate update and you can always see if the result matches your expectations. And I think if we have something like this, we can write it like so. And then I think, wouldn't this be like just 2 times this thing? So yeah, looks even like a little bit easier to read. And I think we don't need the auto breakers for this. And I think the rest, I wouldn't know how to simplify this. I guess ChatGPT does this nowadays, but yeah. So good enough. This works for me. And we can just convert this into shader code. So I still don't know why how to get this outer radius here. So but I assume with these kind of things. Okay. So yeah, let's try that. So we have our little gizmo here. I'm not really sure if I like the shape of this gizmo very much. kind of like hard to read from the side. And so we have a bunch of options here right now. There is this sphere gizmo, and the sphere gizmo is like, look at this. So like this is a lot of, it adds like a lot of radial points and pens these and draws lines and stuff. I think it would be easier to just have a sphere points, and then just draw some points. And this is our new gizmo here. And maybe we add a little bit more so we actually see like what's going on. Oh, is this easier to read now? Maybe not. Maybe not. Huh. Okay, I think the other version was easier to read. Yeah, kind of. Gizmo styles are annoying. I really have to say they are annoying. I mean, one thing is I don't even know why there is like this. Because we had different modes here. So we had a sphere mode and we also had a square mode. And probably later we should have a bunch of other modes. We want to start with let's start with the minimal function set here. Okay, and now we apply this transform matrix. And we wanted to have a bunch of these. So does this actually, it has a radius here, which means if we group this, and if we take the falloff, and multiply it to the radius, what was the formula? We take the radius 1 minus f. What the heck? So we take, let's collapse this, and this goes into the 1. This is 1 minus f. This goes into the sphere radius. And we adjust the color to something else. Okay, this is definitely not what I expected. So, or maybe it is. Maybe it is because if it's I think it needs to be half the size. That's true. It's also like the default here is half the size, and I think there's might be a problem. Good question. So let's do the second. So this would be the outer, I guess. And let's build the inner. And the inner one was f plus 1. Add. We hold control to duplicate that. Oh. Control to duplicate the connection. This is 1. Let's go to the radius. And let's reset this to 1. And now if we increase the falloff, it should go. And if we increase the volume scale, okay, it scales. I think if we look now from the side, it should be possible to actually see the result of this. So as soon as we... No, I think this starts too early. I don't know why this is. Probably, obviously it's not working because yes, we have a Gizmo here, but we didn't apply the Gizmo in our shader source code. So we need to apply the same formula here. And I wanted to make sure that this is roughly okayish. So if we say the size of this thing is 1, so now we have the question whether or not the sphere is like twice the radius or not. And I think it should be half of that. So let's go into the thing here, and we halve all of them. So this is basically half, and here we just we take the original radius. Wait a second, we have to. Is this? Can I do this before or after this? I don't know. Multiply. Let's check this. So maybe half it first. No. Boo. So obviously we have to, let's undo this. We have to multiply it after that. Multiply, duplicate it, and insert it in here. Come on. Why can't I multiply it? Yeah, there we go. So, okay. Tell you mathematics. Bad. So, and we, let's make these guys a little bit less opaque and still give them the same color here. I wonder, maybe it would be interesting to have some kind of visualization of like what's inside and what's outside. So we can actually see how these, like if we flip if it's flipped, then we would see a difference. Oh, this is tempting. But yeah, not now. Okay, so we did this. Now let's reset the view here and zoom a little bit out, and then let's fix the shader code so this actually does what we expect. In this case, I would expect like the circle to be completely only here in the lower ranges when it's actually inside it. So we go into the shader code. Let's move this towards the right. And then basically this length is the X. And this needs to be like whatever formula we have here. So let's call this X. Then, let's call it D for distance. Now, what do we have here? There is like the main thing is this T. Let's move this over here. So load T equals D plus the radius should be, the radius is always 1 because we are not scaling this thing. Oh, wait a second. Ha! Ha! This doesn't work because I don't have a radius here because we are working with the unit sphere because we are transforming the coordinates up there. Ah, stupid me. Which means we cannot simply have this proportional falloff thing. Okay, let's assume the radius would be 1 for now. Float r equals 1. And just convert our formula there. So we have the radius, then we have the falloff -1, and then we combine all of these and divide this by, so I'm there, 2 times the radius by falloff. And then now we have the smooth step. Reload. Let's call it b equals smooth step 0, 1 t. And the good thing is that we don't need this anymore. And the units there we also don't need. And this is our new blend factor. So let's see what's happening. So obviously we have to think that the falloff is inverted. So if we switch it over there, so this seems to be working. It's either inside or outside of the volume. So this part works. And we see that the radius seems to be twice the size it should be, which is this whole thing that we are using the default radius. So now we see that it's like there's a little bit of adaptation there, but no adaptation outside. So this is also nice. So if we flip this around, this also seems to be working okay-ish. And then earlier we had like this parameter, like the strength, but right now we don't apply that. And I think we could apply it to the result of the blend factor here. Strength. Multiply this here, and then if the strength would be 0, then nothing would happen. If the strength would be 1, then the default thing is happening. Move this a little bit up there. And if the strength is very low, then we should see like a more graceful ramp between the falloff thing here. So far so good. So like it's, you know, like, it seems to be working also like from the scaling factor. So I'm slowly getting in here, and then if we're moving out again, so this is where the effect now applies. And then if we flip the falloff, then we are reconstructing only like the thing inside this. So far so good. So now the problematic thing is that the problematic thing is that scale doesn't work, which is bad. Because once I increase the volume scale here, we should also increase the radius of the thing. And we can't because we don't really know what's the distance here. I think, okay, we could assume that maybe we could just take like a unit vector and use this as the falloff radius. And probably this is also what we do because the falloff radius would change once we squeeze this. So let's try that. So if we have we take the load 3 fall off in how did we call this other in volume and you might remember earlier we had a discussion whether we are using a position or a direction, and in this case I think this is a direction. This is the original falloff. We're using the same length for all axes. And we're using XYZ components. And this is the falloff. And now we could do all these things for vector 3. But I don't know like how we combine the end result of this. So let's just take like this thing here, like take only one axis of this. This is actually, did it make a difference at all? Let's check if there are any errors here. So, so it compiled it, which is good. Maybe clean this thing here. Put this back here, enable gizmos. And so maybe this will be a one after all. We take this, we transform the falloff. The falloff is this guy. Maybe we have to use the inverse transform. Oh, this is bad. Difference. Makes no difference whatsoever. I mean, maybe it's already working. Reduce the strength drastically. There seems to be like an inner circle that is like starting with the fall of range here. Yeah, maybe it's already working. I'm just too paranoid. So if we can increase all this, increase it quite a lot. And the circle is being restored. And we move all these guys, then it goes back again. And if I change the strength to this. So maybe it's working and I'm just too intimidated. I mean, we can also, let's increase this to 1, to 2, twice the size, and do the different check. So if the falloff should be a super hard edge, then we should see some drastic changes. 0. So maybe if you do this super small, then moving this. And yeah, it's a super hard edge. So actually, maybe it's working after all, and I was just too timid to see that it's working. Okay, nice. Oh, interesting tentacles we have here. So let's take a sip of coffee. So there's another thing. So like moving this is like kind of annoying. I think it should be easier to have a gizmo there. So let's add this as well. So to do that, or actually, yeah, it's a good idea to go in there anyways, because we have also distance mode, and of course, like 0 and 1 is like, this is not a good parameter value for the Gizmo mode. So let's jump into Rider and let's find our reconstruction force. Like, we have a bunch of obsolete modes in here that we maybe one day will add. So then we have a primal enumeration, and this will be the distance mode. And I use plural because the parameter name is already called distance mode. Yeah. And then the first mode is use point positions, use points, use target position. I think probably good to have the position in there. Position. And then we have to use these modes. So we go in here and say the map type equals type of distance modes. So we compile, and then we get our little drop-down thing here, which is much nicer. And I think the default should be target positions because it's easier to understand. Set as default. Then I think the falloff thing here, this is like kind of awkward. It should be, I think the default should be, if this is called reconstructive force, then with a positive falloff, it should be inside and not vice versa. So we should change this behavior. So we go in here and say falloff and check where falloff is used. Oh, wait a second. Why? Like this is bad. Why are we using falloff there without this volume being scaled? So actually, we are not using falloff at all. So I think. Wait a second. I didn't think this through earlier. So shouldn't this be an F? And if this is a very low strength, this be? No, I think this was fine. I think we don't need this thing. So then where this unit for? We luckily don't need this anymore. And the radius we need it. Yeah, I think this is. Can we actually add a const here? No. Const float. Yeah, I think it's better like this. So and we wanted to invert the falloff there. So for this, I think it should be sufficient to just flip this move step. And now if we flip this, we should have the same that as earlier. Okay, next thing is we want to have a Gizmo there so we can actually direct this guy around. So to do this, we have to do a bunch of things. So to be open, to be honest, I even can't remember this all the time, so I always copy it from somewhere else. So let's, for instance, take like the radial points. And the radial points, so you know, if I click this, I get this little Gizmo here, so I can move the radial points around. And I want to have the same thing when I'm clicking on the reconstructed force, so you can move on the center. So let's see what we have here. Like the third thing is that the main output should be a transform callback slot. So okay, should be doable. Zip. Zip. Then we need to implement these guys. So there's already like somebody already did a mapping. Probably me when I was doing the from which operator did we derive that? From the force, from the surface force. So the surface force already had this. And I guess maybe that's already it. So let's compile this. Oh no, did it crash? I think it crashed. Boo, boo. Modified. I guess it crashed on me. Stupid thing. Where's the debug? Build. Debug? No. Ah, here. Oh no. It crashed. So we don't want to submit a crash report. So the transform callback. Base update action. Yeah, I think this I think, damn it, we forgot the constructor here. Boo, boo. So like this goes in here, and this is the constructor for this operator, and the output is this guy. And then we resume. The tool shuts down. And then once this the shutdown is complete. So like how long can it take to shut down? Okay, let's stop this and let's start again. Or maybe it didn't. I don't know, it crashed. Yeah, but it crashed. Okay. Starting up again. Okay, here's our little effect. Let's move this into the background. Let's enable gizmos. And if we click our reconstructive force, and if we zoom out, there's our gizmo. Look at that. And I guess maybe we should also, so like where's actually the circle here? Okay, here's the circle. So, and here's the reconstructive force. And then if we move towards the circle, then we should be able to reconstruct it. Yeah. Okay, nice. Okay, I think this is a nice progress. We could add a bunch of presets, but I think this is good enough for now. So let's go back to our to-do list here. So we have the spatial adaptive reconstruction effect. I think we did that. So there, we done that. Add option to use distance to target position. We did that. We implemented the correct falloff radius. And now we can go into the other effects. So let's actually try to do some interesting things now. So for instance, what we could do is we could take the let's try to use cubes instead of radial points. So instead of drawing points, we say draw mesh at points, or we control click to duplicate that. We take a cube mesh and we pipe the cube mesh into our draw mesh at points, and then we move this up here. And it's teeny weeny points. I think because we have this use W for size thing here. So if these are that's big points, big cubes. But if we move them down a little bit, we see, okay, there's stuff happening. Actually, now that I think about it, we had this derived point orientation from velocity. I think like now, soon there will be the time when we actually should also add that. So that so currently the rotation looks very homogeneous, and we want it to be moving towards the actual turbulence force. So, but back to the topic. So now what we can do is let's say we build a cylinder. So earlier we used a cylinder mesh and used the vertex position as points. But I think it's more interesting, or should work just as well, to say we have radial points. The direction of the radial points is, so we start at the center. The axis is not towards Z, but towards up. We have a radius of so if we, yeah, let's keep emitting so we can actually build our shapes. Let's say we have 10,000 cubes, and we have let's say we have 20 cycles, and we move this up. So we should have some kind of spiral. So eventually, so there we go. And so like if I'm kind of confused, like how many 10,000 cubes? That's lots of cubes, it looks like. So let's add more spirals. Okay, this is too much. So let's add spirals, like so. It's actually interesting that it now looks like some kind of masonry. What? Interesting. Okay, and if we stop emitting, we should see these guys falling apart. And if we move our reconstructive force, we should be able to actually reconstruct part of that. So currently the force, the strength is super low, but yeah, look at it. We can reconstruct our cylinder here. Or vice versa, if we go to falloff and make this negative, we should see an immediately some impact there. And so currently we have this turbulence force, but then we can use all kinds of forces to break holes into our cylinder. So actually, I would have thought that this would be more disruptive. Actually, why is it not falling apart? Well, it's falling apart a little bit. And maybe if we increase the frequency there and the reconstructive, maybe the falloff is a bit. Okay. So now what do we actually do with this effect? It's interesting that with the fall off, I'm not really sure if I like the behavior already, but yeah, well, we can, I guess we can see something. We will see how this feels, and we can adjust the behavior later. So find like a much smaller amount. Well, it's interesting that they have some kind of secondary animations there at the border. I think I really like that. I guess if we would it's just very interesting to observe these behaviors and try to figure out what's actually going on there. I think just observing that, so we really need to work on like the velocity thing. So this because I think if we would have the velocity thing, we would see some adaptive shading here. So right now, like all these cubes have the same alignment towards the center. But if they would be aligned towards their moving direction, we should see some nicer shading there. So let's try to do that. And we do that by, so let's move this back here, switching back to our graph. And I think this should be a parameter of the particle simulation thing. So let's go in here and say we have a parameter which is probably okay to have a float parameter, and if this is, it's almost like a lerping, I imagine that. So let's make a sketch here. Of course, we do the sketch not for you, but for me, so I actually know what's going on. So so let's say we have white. So we have a cube here, and we are get a bit easier. So let's say we have a pyramid. Easier to discuss a pyramid. This is the center of the pyramid, and now if we have a certain velocity, let's say it's moving up there. Let's say this guy here, like this is the peak of the pyramid. So let's take this guy and combine them into a shape. So I imagine this float parameter, if it's 0, like this guy will move like this. Actually, no, wait, it will move like this. And like it will move towards the current velocity, but it will not rotate. And then if it's 1, it will immediately go like, okay, like this is my new direction here. So it will immediately do like this guy. And so let's make it like so. And if it's not 1, then it will take a while to get to this new rotation. So let's basically let's take this guy and also merge the center and move this guy here. So we can move this around, move this there, and say this is so like this is the final result. The center will be on the velocity line. Maybe take another color here. And this will, in the middle of this line, will be half the rotation. And this will be half the rotation. So something like this. And so the parameter basically defines, I want to do that. It basically defines the length of this. How long does it take to accumulate target acceleration? And it might also be like the length of the acceleration should also be we should basically use the speed of the direction also to adjust it. So if it's just floating slowly like then nothing happens. But if it's going like then we should immediately start like using this. Let's try that. So it can't be too hard. So we are in particle simulation. We add a new parameter, add input parameter. It's a float, and we call this orient towards velocity. It is a peculiar name. Orient towards fly. Move direction, orient towards. Okay, let's. We can always rename parameters later. So we drop this into our parameter buffer. We open the shader. We add this as a parameter. So peculiar arrangement there. Float orient towards velocity. There's all kinds of like legacy stuff. Don't even want to think about this now. And I guess somewhere in here we could say, okay, obviously, like if the currently we store in W whether or not the particle is valid. So once if we are emitting at the beginning, we don't want to see like all the potential particle positions inside the buffer, but we only want to see the emitted ones. That's why we initially reset them. If we reset, then we write W into W, not a number. And then we do nothing if it's not a number. So to be honest, I don't even know if like something like this would be faster to still all do the computations because we are in a shader and this does branching. But yeah, premature optimizing. Let's get it running first. So now we have our new parameter and we could say, let's start with, okay, no matter what, the orientation is towards forward. So we can do this by, we do collected points, GI, rotation equals, there should be quaternion from look at, and this is probably the velocity. So let's do this down there. We actually have the velocity already. And yeah, but like this is like there's this whole thing with orientation from a target vector. This only works if you have an up vector. And don't get me started. This is horrible. So the problem with this is, so if you think about it, if there is, how do you explain this? So like if you, let's go with white again. So if you have a coordinate system in space. So once again, this is X, this is Z, this is Y. And then you have a vector. Let's say the vector goes here to precisely Z, X, Y, 1. So like this is our vector here. Get, I don't know, like whatever, like some kind of color. Then, okay, this is obviously how you would return something towards this. But this rotation around this vector is undefined. And the only way you can actually figure out this rotation around this axis here is by having like a secondary vector, in this case the up vector, and then doing the, I think what you normally do is that you take the cross product and then the cross product. So this is the orientation here, like this exit is coming out of this. So this is the alignment and the flyer would be like this. And this works really nice until like you look up to Y. So if things fly straight up, bad things will happen. And I don't know how to mitigate this. I think a lot of people probably know. I don't. So look at that. I think we already it already compiled our thing and it did stuff. I'm confused. So why? It looks definitely interesting. So like what's even like going on here? So like what we see is outside, if there is no velocity, then the rotation is broken. So obviously this is not a good idea. We can really see outside the circle, the velocity is completely broken. It's also hard to see whether or not the direction is correct. So let's do something else. Let's go out here and say, instead of drawing cube meshes, we also take these points and then we repeat other points at these points. And there is an operator called common point sets, and this has a bunch of point definitions, and there is a definition for arrow Z, and we can repeat at these points with the correct orientation like a bunch of other points that define an arrow. And then we can draw this as lines. And let's make them blue because they are pointing towards Z. Maybe like a little bit half transparent. Maybe we scale this down a little bit. So what do we see there? We see that I'm kind of confused. I would have expected all these things to have arrows. Like even like the flying ones. Maybe it's too small. Increase the size a little bit. Huh. What? Why don't they have and it's the same? They are coming from here. Oh, look at the teeny weeny arrows. I think the problem is that quaternions, my love of quaternions. So I think this guy, I think it needs to be normalized. No, didn't make much of a change. And I think currently we are in this mode where I think this will also apply target scale. Yeah, I think it will use the W parameter to scale the target points, and this is not really what we want. Actually, let's quickly go in here and transform these points and move them a little bit forward. So you see, like if I'm moving this half a unit forward, then they are. Oh, it's not static. Why is it not static? Flop. Sometimes they are. I think if they're reaching the, appears to be, if they're reaching the border, they do some really strange things. I mean, besides this, it seems to be, okay, maybe not. Yeah, it's like really, they are not really static. Maybe we can, I wonder what happened, just very playful. So let's say we have less of these. And less of these. So only like 1,000 or something. And then if we take these guys here and have like a point trail. So now what we should see is that maybe like also decrease the line size a little bit. Yeah, we can better see that there are inconsistency in the movement there, which I don't really know why this is. And also we should be able to visualize this. Go back to this guy here. So since we have this point trail, we can actually add a group here and draw this points maybe with orange or something, so we see like where they we can follow their path. At least I thought I could. So we should. This is a bug here. Yeah. I have to fix this, but I think it's not super straightforward. So so we now see we can now see how they are moving about. So let's quickly disable the reconstruction force here. So we see how they are moving. Actually, it looks kind of pleasing. Let's pause this. And then let's move around and see if this is really the thing that we are expecting. I would say not even close. Because what I would have expected is that they're moving towards here. And this is where this blue arrow should point towards. I mean, it's a beautiful shape, but certainly not the shape that we want. Boo. Boo, boo. Boo, boo, boo. So what should be possible is, so to figure out, let's start with the figuring out whether or not the point orientation is actually correct. So let's take one of these points here, or let's take all these and visualize these points and their axes to figure out whether or not this is actually correct. And we don't need the indices, but we want the axes, and the axes should be large. And actually we don't want to have the trail points, we want to have the original points. And then it should only be the last one that we see. And my expected behavior would be that Z should point forward. And it doesn't. So at least like it's hard to see, but the Z-axis always points toward the arrow. So like the arrow thing is correct. So this works. And we also see that that this whole like thing, the actual rotation seems to work, but not the acceleration. So let's try something else. So let's say we go back to start with, let's clean this up. It's not too confusing here. Refinement, this reconstructive force, we have the radial points, and let's move this, clean this up a little bit. So so if we would not use a turbulence, maybe the turbulence is a thing. The expected behavior if we just move up, direct the directional force up, then all the arrows should point up. So let's tip. So now they are let's move to the background. And here it seems to be much better. And here it doesn't work at all. What the fucking what? So let's emit from scratch here. Emit. We don't see any blue arrows because What? So we take this, we don't use W, which is like the, and this is the output. So let's maybe look at the W values here. And W is something weird. Did we set W here? No. Speed. We don't set the original thing. We don't use aging. I think the I really have to add the proper enumeration for this guy here. So let's do this. Damn it. So let's go to particle position, particle system, particle simulation. And we already have the set modes, but we don't apply it to the dropdown. Map type of set W modes. Okay, and we keep the original. Okay, and the original should be 1. Why is it 0? The heck? Emit. Okay, it's 1. Okay, so the next thing is I would have expected these guys to yield into cubes. Why don't we see these guys here? So we only have the directional force. And so let's check if we use these guys. Still don't see cubes. And I think there seems to be a problem with something is wrong with the radial points here. So you offset them. Huh. That's very peculiar. So let's look at this guy here. So this is a default cube, all the default settings, all the oh, wait a second. Don't dare. They are. Okay, so stupid me. We went just too far up. So, and then these are playing all the time and we emit points all the time. They're moving up there. So now if I use the particle simulation and draw these points, I would have expected to see cubes there. Are these cubes? No, these are points. And maybe also we don't see an arrow there. And we don't see the point positions, which means that the orientation seems to be broken. So yeah, so we write an incorrect velocity in there, and this is because probably no. I guess the velocity is just 0. Okay, wait a second, like this is, so we need the velocity anyways. So let's move it up there. Let's have the drag thing up there. And I think no matter what, we can already write it back into the simulation buffer. So that should do the same thing. Now, if we have we can now compute the speed here. And for the speed, we probably want to have like this guy. So this is the speed. And speed is already taken. Where are we? Ah, it's not taken. Load. Speed equals this. And okay, probably put it here. So, and once again, so then we see it. So let's say maybe the speed is 0 currently. If speed is teeny weeny, we don't do anything, otherwise we apply the rotation. Yes. So the problem is that so currently we are always emitting. The initial velocity is 0 because we don't set the initial velocity, we reset it actually. And then it's quite correct that from a 0 length vector we can't compute a rotation. So this is completely valid. So let's make this a little bit smaller. So we should see our points moving, and this looks as expected, I would say. Now, if we take these radial points and change their orientation, I think there should be this orientation angle here. We see that the simulation points look correctly if we rotate around the z-axis. Okay, if we rotate around how do we have to rotate? So I guess this looks okay-ish. Now if we actually, it's a nice example. So if we don't do anything here with directional force, and we set an initial velocity, and then we stop emitting, they should move outward, and we should, if we now pause this, we should see an outward direction. And we should see arrows pointing towards the yellow line. So far, so good. Okay, if we now let's reset this. Reset. if we now also apply upwards movement. Interesting, wait a second, like this looks totally off, because I would have thought that this would be like a gradual increment in like in direction. Value only emit every once in a while. So why isn't this like a movement that's going like whee, going up? Directional force is up. If we reduce the amount here, it should still be it's probably because we have there's no dragging. So let's see how this is being implemented. So we have the direction, the random amount, go into the shader. Oh no, don't want. And we see that we add the velocity. Huh? Shouldn't this be like an acceleration curve, because it's like getting faster and faster? Like so for instance, if this would be gravity and it would pull downwards, I expect this to be, would have expected this to be like some almost like a curve or so. But it's a line. And so there is no drag. So if we increment some drag, then it would eventually slow down. And then I can see how the initial force is being reduced. Huh. This is like not what I would expect it. Line points. Oh. I think I will pause the recording here, because watching me figuring out like why certain things are not moving is probably not super exciting. And once I figure this out, we can jump into actually building more beautiful things. Yeah, but if you actually stuck out for that, kudos, respect, and yeah, hopefully see you in the next video. Bye.